lead at Intel Bangalore, and he is having more than 7 years of experience in semiconductor design industry. Now, I would like to hand over this session to Uday garu.
Yeah, thanks for energetic introduction, Krishna. Sir. So, yeah, hello team. So today I would not like to waste my time. I would like to directly jump into the content because I have lots of slides actually, like I wanted to put in. So, uh, if everything is fine, I'll just jump into the discussion and share my screen. Shall I start?
Yes, sir, you can start now.
Okay, thank you. Yeah, most probably, like I'll be explaining the whole backend flow now, and at the end we'll be having a glimpse of packaging today. So it's more than packaging, right? It's more important to understand the physical design aspects in the first place. So so basically, a chip design. It's what you might have been through some previous discussions quite a while. So yeah. So even in the first session that you have gone through, maybe RTL to GDS flow. So now we'll be discussing specifically about the physical design stage, where this physical design was one of the stage over there amongst many. But now we'll be only discussing about this precisely. Is my voice clear and audible? Can somebody just let me give me some feedback regarding my voice? Hello.
Yes, sir, your voice is clear. Hello.
Hello.
Yes, sir, your voice is clear.
Hello, Krishna.
Hello, Uday, sir. Am I audible?
Yeah. Hello. Sorry, it was connected to some Bluetooth network. Is my voice audible? Clear and audible now?
Yes, sir, your voice is clear and audible.
Yeah. Okay. Thank you. So now the chip design. So what is a chip? So as we all know, the chip executes complex functionalities. Many applications and many applications itself
Sir, excuse me, sir.
Yeah.
Please keep slideshow for clear visibility.
Okay. Yeah. So, so the chip is nothing but, as we all know, it's a hardware that implements highly complex functionalities, and a lot of softwares now that we are able to see, the web applications or mobile applications, they are nothing but, the software is nothing but a set of code. A code is nothing but a group of instructions, right? So that need to be executed, and amongst these instructions, there will be a lot of you know interlogic, which instructions should be executed first, or which set of instructions in the code must be threaded if there is a multi-threading. So these kind of complex process steps, which finally, if you deduce, they comes to basic arithmetic and logical equations. Any process, any application, if you take, and any any code if you take, and any line of code if you take in that particular application, I'm talking in the level of software. So that if you deduce that the system deduces into the basic ALU, arithmetical and logical equations, and there will be an ALU inside the process that we all know, and that will execute those steps. So to and we can find that all these process steps are being controlled. What should be executed first, and where should it go and store, and the memory control unit will be there, and MCU, the memory control unit, will be there, which will be controlling the read and write operations um, between the processor and the memory, and cache, SRAM, DRAM. All these hardware components that I'm talking about will be are very generally available on a chip, and these are all required to execute a complex function. That's on the top level. So nothing in this world can run out of chips, because everything should run on top of chips. So that's the importance, and that's the demand we have for the chip design. And yeah, so that's why the educational base must be more enhanced, and should be upskilled to reach the industry level training, so that the students who will be graduating from the colleges uh, must meet the gap, or must hit the bar of the industry level things, because software guys will be probably very much ready to the industry by the time of their graduation. But when it comes to VLSI, they are not up to the mark. It's the general case. So that's the reason we all are having this, and yeah, hope in future we find students and faculties meeting the standards of industry. So let us get into the point of the discussion now. So now you are able to see the PPT here. So yeah, there will be a level of designs, in the RTL, while initially the RTL guys, the front end guys, as you all know, the ASIC design is broadly classified between RTL, design verification, and then physical design. In physical design, you'll be having synthesis and PNR separate. So the RTL guys, initially there will be an architect. He will be he'll be describing the spec. For example, if it is a DSP chip, so you would, if you would want to interpret, let us say, if you would want to interpret the image recognition hardware on a chip, right? So what is the logic that you need to write? Let us say you're using the fully connected neural network, then it would be an algo core, where you'll be writing the logic in the RTL to implement the FCNN, and then the outputs and the inputs that require memory, on chip memory. It will be having RAM, and you can see the CPU here, right? So I'm just picking up a random example of this implementation of an FCNN on chip. So it's a very good project idea also, like, if the students want to implement. So here you can find the CPU. Let this CPU be the logic executor of FCNN. Then the inputs to the CPU and outputs to the CPU must be stored in the RAM, in the memory. So we have a memory, and then for the read, write, and fetch cycles, we have the interconnect. So that will be the bus. So these are the top level hierarchical components that will be defined by an architect to estimate the spec. The spec will contain the bus width. The spec will contain the clock frequency with what CPU functions. Like, it will be in gigahertz. Basically, if you see the clock frequency of the current process of Intel, it is reaching to 4 to 5 gigahertz, approximately, and more, and yeah, there and yes, there is also the spec also involves in the ROM size, and also, you know, and there will be internal specifications. Okay, so if you want to customize, if you want to customize your chip for higher for a better performance, then you would want to increase, for example, the memory density of the RAM. Okay, so currently the best memory density of the RAM is like 4 to 5 gigabit per millimeter square. So if you have a, Apple Bionic processor is about, I think 1 year back, it's 1 centimeter square area it's having, and yeah. So imagine 4 gigabit per millimeter square is the memory size. So in 1 centimeter square, how much amount of memory you can embed? So these all are the aspects that would come, while the architect guy is specifying about the memory, deciding the spec of the chip and the bus width. So what type of bus you want to use, a 64-bit bus or a 32-bit bus, or, you know, 120, 128-bit bus. What type of bus you want to, the more the bit width, the more parallelism and more faster the fetch will be. Or else if you reduce the bus width, right? So then you need to have multiple cycles to get that particular data from that memory location and send it to the processor. If you increase the bus width, it might not, it might not even pinch you a bit while you're doing the front end design. But in the back end, when you go to routing, it will be very, very complex and tedious for the engineers to perform that routing with that much bus width. Okay, it occupies a lot of metal resources. We'll be discussing that later. So that's how the architect guy starts, and the register transfer level. That once the architecture is defined, right? No code is written from scratch. Everything will be, predefined modules will be there. They'll be integrating all the modules, and we'll be having the register transfer level code written by the front-end designers after the architecture is given by the top level architect. And here, all the sequences and the functions and the logics will be written. So there will be basically, as we all know, behavior, gate level, and data flow level. But for physical design, physical design friendly, um, if the for the front end RTL to be friendly for the physical design, because RTL is one of the input to the physical design. Data flow is most friendly, for the tools. It would be very easy to implement, and very less number of sanity will be there if you use data flow for physical design. So once the RTL is done, so we do a design verification and verifying all the corners and ounces of the logic and the functionalities. So we need 100% coverage, right? There, so all the edge cases and corner cases, must be covered. And once the design and verification is done, then we go with the synthesis. So what is synthesis? So now, so we need some a brief sort of explanation about the synthesis. I would like to make use of the paint for that. So, so basically, um, so we have an RTL which implements the logic, and we have the logic, and we verified it using design verification. Now we want to realize the hardware. So to realize a hardware, so we also have a modeling called gate level model. So this gate level modeling, this RTL will be converted into the gate level netlist. RTL will be in either data flow, or it will be either behavior. So the for loops, the if loops, the case statements and whatnot, the switch case statements and if and if else, the for loops, and yeah. So all these sort of the code constructs that we basically find in C and Python and all. So these will be converted into hardware. For example, if you use a for loop, it might convert into a pipeline counter. If loop, it might be an encoder or decoder. If you use case statements, it might be a multiplexer. Okay, like if the case statements will be like a case, and you will have I don't know the exact uh, exact notations, but it will something look like this. If the particular bit is 000, then what should happen? If it is 0001, then what should happen? This is what the constructs of the case. So this will be something, so if you consider this as a block, okay, so then this block output will be given as an input to a mux. And if you consider this as a block, okay, this as a block, then this block's output will be given to the one of the input of the mux, and there will be other blocks as well, and you will be having maybe 16, as I gave 4 as combinations, and you will be having 4 select lines here. So whenever the input is something, the output will be accordingly same. So this is how your RTL. This is RTL. So this is how your RTL will be converted into. This is gate level. So in gate level, how this would be written. So we'll in gate level how it would be written. So I'll be showing that here. So this is the gate level. Okay, you'll just having the logic gates, and I think I have. I think I have a small coding interpretation of it. So this is the very long description that we always see. Okay, and if and else. So what should happen if it is reset, and if it is reset, then and if not reset, like if reset signal is not on, then what should happen? That is given clearly there. And yeah, of course, every gate is now that we are using the CMOS technology. We would discuss this a bit in the next slides. So this is what the flow of physical design. So you do the synthesis, and so once you convert it into gate level, so you will have to retain the functionalities. Okay, so you will have to retain the original functionality even though when it is converted to gate level. So you convert it to gate level. That means you just converted a raw code that is almost equivalent to C, very log, to something. You mapped it to a Boolean algebra basically. The raw code, which is something equivalent to C, which contains for loops and if loops and case statements, you mapped it to Boolean algebra. So now so once you map into Boolean algebra, tool might have optimized some things, and we'll see what it optimizes. So during this optimization, it should never disturb the functionality of the design. So the intent of the design and the functionality of the design should not be disturbed. So that's even one inverter can literally be a reason to fail the chip. Okay, so I'll tell you how. So let us say you have long nets. Okay, you have long nets, and if you have long nets, there will be long delay. We'll be discussing that. So if you have long delay, the tool will try to add some buffers on this nets to reduce the delay, because it is as similar to as we will be having the repeaters among the transmission lines, electrical lines, right? So we'll be having repeaters. We'll be able to see that on highways, on the right and left side of the roads. So every 2 kilometers we'll be having repeaters, so that the voltage level would be amplified to the initial. So this is also the same. The buffers will be added buffer is added, it's okay. And the inverter pairs will be added. Sometimes what will happen if there is no space, if let us say if one inverter is added instead of two, what will happen? The functionality will change. The A should go as A, right? So whenever a tool adds inverter, it should add as an inverter pair. If it adds, if it adds only one inverter, so this A will not go as A, it will go as A bar before it reaches the flop. So that will be a showstopper. It will just ruin the design. So you need to have a formal verification. That's called formal verification, where you'll compare the RTL and you'll compare the gate level netlist, and you will check whether the functionality is retained or not. So the tools are specifically designed for this purpose, and it will be able to do so. Okay, so next, yeah, so we'll be having pre-layout STA. So it's like zero wire load model and maybe unit, zero wire load model STA. So we'll be having that, and the timing is okay. After the synthesis, then we'll be going to the floor plan design. It need not meet. So timing need not meet completely. It should be a bit better. Even if it violates, it should be better. So we'll discuss what is violation and all. What is time? What are different types of timing violations? And why do they occur? We'll be discussing that. So then we'll be doing the floor planning and routing, PNR stuff. Now, once this is done, so we'll be getting the layout. So what you do after the layout is that you need to check for the design rules. So once you do the layout, so you basically give the GDS file to the TSMC guys when the shuttle is open. So then what happens if they'll be having some rules? If those rules violates, then the fabrication will happen in a wrong way. So for example, there is some. So this is a wire. So basically, when you look into the design, this wire will be very symmetrically rectangle. But when you go to the fabric, when you really fabricate, it will be something like this or something like this. So that's why you could see a bulge here. Okay, let us say there are two wires here like this, parallelly. They are parallelly going the design, the router. So if you don't, so the TSMC guys will give you a rule deck file. Okay, so that rule deck contains what is the minimum distance between these wires. What should be the minimum distance between these wires? Even though in our design, if we find them not intersecting each other, what happens if two wires intersect? It's simply short. They'll get short. This is one signal, and this is sig1, and this is some sig2. And if these two get shorted, both the signal cuts, and the transistor gets nothing, or it might get very much high voltage surge, and it might even get damaged. So this short should be avoided. So that's why they'll give some minimum and maximum constraints as a rule link. We call it as a rule link. In this rule link, we'll have those constraints. So in the design, if this doesn't meet, it will show us as an DRC error. Okay. So we need to fix this error. If we do not fix, in the design, it will be very good to see, but once it gets fabricated, things will mess up like this. So that's why physical verification is done after the physical design. And then the timing. Okay. Timing also must be met, and we'll discuss the impact of timing, how it influences how it drives the design. The timing is the most important thing that drives the design. And yeah, before going any further, I would just like to say that physical design is all about PPA: power, performance, and area. performance comes with the timing, and so if you improve the timing, you can operate the design in the more speeds. Power comes with the voltage. How do you manage? How you manage voltage? It's not like just reducing the voltage level to reduce the power, but you should also know when to keep the gates on and when to keep the gates off. Like, see, if you have a house, right? In your house, let us say, so we have two houses. Generally we get 230 watts or 225 watts, something like that, volts. So let us say this house is getting to 30 volt, and this house is getting to some 150 volt. Just giving an example. Just give me a second, guys. Just give me a moment. Yeah, sorry for the interruption. So this house A is getting, let us say, so house A is getting 230 volt and house B is getting 150 volt. So which house consumes more power? It's obvious, which is getting the high voltage consumes more power. Okay, but let us say this high voltage guy is using all his components very organized manner. Like he's not unnecessarily owning all the switches, and while there is no use, he's switching off, turning off the lights and fans and ACs. But this guy, his he is now he's very neglect. He's demanding very he's showing lots of negligence while it comes to saving the power. So then what happens is is letting on the lights and on the fans unnecessarily. So this guy, the average power distribution, if you take as a graph, right? So what is power? It's, let us say this is time and this is it's voltage. I think this guy, this is for if A will be like this, maybe for a unit time, and maybe B will be like this. This is some 150, and B will be 230, but B's will be like this. Maybe if you calculate the average power, it is I think the power is something related to P equal to VI and V of V into I of T, and then I think if you integrated something with something maybe V square by R, then P equal to V square by R. So if you try to do some mathematics and calculate the average power, this might be more efficient than this, even though the voltage is high. So it's not just reducing the voltage level, but it's also how you manage the power. So that comes under this stuff, and also area. So you need to use solid hardware. So you need to make sure your hardware doesn't exceed the area, because even 1 millimeter rise in the length or width, it costs a lot. You know, it'll impact a lot. It's very 1 nanometer also very important in physical design. So that's all about the introduction. Now let's get into the stuff. So you do the logic simulations here, and once the logic is met, you'll go further with the design verification, and further you'll do again the simulations, and then you'll do the synthesis. And let's come to the synthesis. So in any code, any functionality can be mapped to Boolean algebra. That's the beauty of Boolean algebra. And then the synthesis, you'll be having the gate level mapping of the design like this. And in synthesis, you will be having some optimization stages. Okay, these what type of optimizations will be happening? Let us. So did we include that? Yeah, we will come step by step. So um, this is about synthesis. So first it will be circuit description. You'll do the logical synthesis. So before getting into the synthesis, I'll give you a brief, and then I'll discuss about the inputs to the synthesis. So in synthesis, what will be the inputs? The input will be RTL. Let me tell you that. The inputs to the synthesis will be, we'll take some new, I'll start. Okay. So the inputs to the synthesis will be RTL, .lib, library files. This is enough if it is a logical synthesis, and there will be LEF, TechLef, and these files, and SDC. So these will be the inputs to the synthesis. And most importantly, there will be two types of synthesis. One will be logical synthesis, and the other will be physical synthesis. This we'll be discussing a bit later. Let us concentrate on logical synthesis. So ultimately, let us say our chip is just this. Okay, we have two flops. We have an AND gate. Here we have an OR gate. This AND gate output is going. This is B pin. This is Q pin. And this is CP pin. D, Q, and CP. Okay. So you have a gate level netlist. Okay. So from the RTL, you got a gate level netlist. So what other information that you will be getting from the synthesis stage? So in the synthesis stage, you will be getting area of the design or the cells that are involved, of the hardware that is involved, and you will be getting time. Okay. So for the tool to calculate the area and time, the tool needs some inputs, right? So what would be that? So to calculate the area, it requires LEF. LEF files. LEF is nothing but layout exchange format. Okay. So in the LEF, you have two types of LEFs. So one is standard cell LEF and macro LEF. Okay. The standard cell LEF. What is a standard cell? So I know, in my experience, the standard cells I know are AND gate, OR gate, NAND, NOR, XOR. These are all the gates that will be designed by a standard cell layout engineer with the TSMC layout rules, and would be selling it as an IP, as a a bunch of package to the physical design teams so that they would implement the physical design. So these are all the standards like XOR, XNOR, and NOT. And there will be AOI also, special AOI cells, and or invert logic, and OAI also, OIA or OAI. These are all the standard cells. We have DFF, that means D flip flop. So these are all the most generic standard cells that we find in the design. That means we can assume that the whole complex chips that we are seeing, complex, and the complex process and all these things are just part and parcel of these gates. So these are the standard cells, such as standard cells, and we'll be having a sort of we'll be looking into it. We have the standard cell left formats and all. We'll be looking in future slides. It contains the pin locations and area of that particular cell. Okay, that's how we get the area of the design. And macro is nothing but RAM, ROM, DRAM. So on chip would be DRAM and SRAM. SRAM is also called as cache memory. Okay, so now these standard cells will be designed by standard cell layout guys, and these RAMs and ROMs will be designed by memory layout guys. So they will be giving them as IPs. You know, any object in a physical design that you look in when you look into the tool will be rectangular or a polygon. This is a very important thing to note. Rect or polygon. Okay, everything will be very symmetric with sharp edges, rect or polygon. Okay. So this is how we get area and the timing. What these guys do once they design a standard cell like this, it will have let us say this is an AND gate. It has 2 inputs and 1 output. Okay, so they will do spectre simulations. This due to these spectre simulations, what would they do? They would let you know what is the delay taken by the input to go from here to here and from here to here. Okay, so these delay informations will be there in the dot library files. Okay, for every cell it will be there, for every even for the ROMs. So dot libs also there are 2 types. Dot lib. Okay, it's also called as liberty file. It's also called as liberty file. It's also 2 types: standard cell lib and macro lib. Okay, so it will be having the information, and the information will be in a stochastic tables. You know, like it will be statistical, and the statistics have the dependencies, and the dependencies are capacitance and transition time, input capacitance and output input transition and output capacitance. So if this much is the input transition and this much is the output cap, then the delay would be this much, because the output cap belongs to here and the input tran belongs to here. So based on the position of this cell in the design and based on how, let us say it is the same cell here, same cell here. So this cell is connected to 2 other cells, and this cell is connected to just a small buffer. So which will have more output cap? This will have more output cap because the capacitance, the wire is splitted here. The capacitance C1, C2. These are the wire capacitance that is being splitted, and here we have the output net. This is C3. So C1 plus C2 plus C3 will be the total capacitance. Here it is just C1. So even though both are the same cells, but if you give the same signal, SIG, SIG, the time taken by this signal to reach this output or charge this particular output load from this transistor like this, it will take more time. Let us say 5 ns, then this will take some 2 ns. Okay. So even though the same cell you're using, but it is in the different situation, and this is in the different situation. So we get the variations of the delay. So the delay is a function of input tran means transition time, and output cap. Okay. So transition time is nothing but, this is called transition time. 10% to 90% time, how much the particular signal is taking to reach from a low to high or a high to low. It should be from 90% to 10%. This is rise time, and this is fall time. Okay, that is a transition time. So the delay will be a function of transition. It will transition time and output carrier. So there will be a table like this. So I'll just try to show it to you again. So there will be tables like this. Then there will be delay values like this. So that's how you get the area and time. And you need to have RTL. So that's how you get the logic or the netlist. So the gate level, post synthesis, you will get a netlist. A netlist is nothing but the gate level verilog dot. Okay. So yeah. Now let's go here to our PPT. So that's how you get the timing, and yeah. So there is something called as SDC. Okay, so we'll be discussing that soon. So once the gate level is done, and then netlist is, you get the netlist, and you will directly go to the PNR. And for the PNR also, we'll have the same inputs. The left, there will be tech left for metal layer information, and there will be dot libs as usual. There will be netlist, and there will be SDC. This is basic inputs. So once you do the design, right, then to do the synthesis, right? So you will get. So you'll need to meet the constraints like this. So these constraints will be typically defined in the SDC. The clock frequency, the supply voltage, even there will be power aware RTLs also, where even there will be something called as low power designs, and in that low power designs, you'll be having voltage islands and all. We'll be discussing that. Have a lot to have a long way in the session. We'll be discussing. So all the terms here that you're seeing are related to STA. Some are related to STA. Some are related to low power. We'll be discussing that. Only so see, the physical design is something that we learned as a lifetime course. I just did my best to bring that glimpse of PD to you, in a single session. We have lots of slides. You can find it in the left bottom. So we need to ramp it up quick. So now, this is the This is the logic circuit. It's the logic level, the synthesis level schematic. We call this as a schematic. Okay. So you can find the green color elements there in this particular thing. So they are nothing but standard cells. Okay. So yeah. So IP. So what is an IP? So that's also there will be a lot of terminologies. Okay. We need to discuss that. The most important when it discuss. IP is nothing but intellectual property. So this can be hard IP or soft IP. Okay. So hard. So what is a soft IP? So let us say there is a company that has a bunch of front end design, front end and guys. Okay. So those guys have written something, really breakthrough. Really did a breakthrough in writing some different code with very optimized code, and which is used in different applications and enhances the performance of that. So they will have to, either patent it or they need to make it as an intellectual property, file it as an IP. So once they do that, the particular software code will be an intellectual property. Okay, so you can showcase this, you can pitch this to various other companies, so that they will buy this IP from you and they will use it in their devices. So they will be able to buy this front end code. That means a .v code. .v. It can be RTL. Okay, they can use this RTL as an IP. Okay, and they can buy that from you. That is called a soft IP. So when they get a soft IP, they can customize your IP. Okay, the code will be visible, the functionality will be visible. They can customize your IP. Example, like if you have idea, Apple is using ARM IPs, soft IPs. So they take the IP processor architectures and all those soft Verilog codes from the ARM, and then they will be integrating it they'll be customizing it according to their performances, and they will, Apple is quite proficient with the chip design than any other companies, the software companies or mobile manufacturing companies. Apple is very very good at customizing its own specs and taping it out. They have their own VLSI domain in the Apple. For example, if you take Motorola, you might not find that demand and that workforce of VLSI happening there. But in Apple, you can find. So this is one example of IP, soft IP. This is called soft IP. What is hard IP? So let us say you have this soft IP and you didn't want to stop here. You also wanted to, optimize the power area and performance, and you have done a physical design on this. You have gone through all the steps of PD, and then this soft IP will become hard IP. So you will be selling this GDS. GDS is the output file of PD that you give to the TSMC. But you can also sell this GDS to some other guy who's trying to integrating, let us say he's trying to do a processor. So he has RAM and he has NPU and he has the bus and he has MCU. He just wants a CPU. Or let us say you also have CPU, you want an ISP or image signal processor. Separately, you want an image signal processor. So this image signal processor, you will be taking it as a hard IP. So this image signal processor will be initially separate code, Verilog code, and this guy will do the physical design of the Verilog code. Okay, and it will remain as a hard IP, and this GDS these guys will pass to this guy. And when he is doing physical design, he will involve this GDS. So he will not be able to change or customize anything logically. Once you harden some IP, once something becomes a hard IP, you cannot alter any logic there. You will be just able to use the hardware. That's it. I hope things are getting clearly understood. If you have any doubts, you can.
Yes, sir.
Yeah. Okay. So once you harden the IP,
Sir, can we use? Can we take a soft
okay.
IP? Can we do any modifications according to our requirements?
Yes. Obviously, you can do so. See, the Apple guys have their internal accelerators and internal. They have their own customized DSP chips and all. Okay, DSP cores, but ultimately they need to integrate into an SoC. Am I correct?
Yes, sir.
Am I correct? So if you have to integrate it, so Apple guys have a customized memory core, soft core, and have customized DSP core, and have customized what neural processing unit NPU core. They have all the customized individual cores that they developed by using their own VLSI team. But now, ultimately, you need to you need to have an architecture that integrates all this. Okay, that integrates all this. So that architecture is given by ARM. So the ARM will give you a void architecture, a void dot Verilog code, where it will have where it will have its own spec. Okay, so architecture in the sense, RISC is an architecture, CISC is an architecture, and if you come to Intel, Tiger Lake is an architecture. Okay, Intel processors have different architectures. One is called Tiger Lake. So, so this architecture you will have to buy it from the ARM, and then you need to modify this soft IP architecture code such that your individual soft IPs will be embedded into it. You got my point, right? You got my point. So, for example, let us say.
Yes, sir.
Yeah. For example, let us say you have an architectural code or architectural soft IP, or let us say let us say you have done everything, but you just need to integrate this particular DSP chip into your RTL. So what do you do? So you check what is the architecture, what is the bus width of it, so what is the frequency of it, so what type of bus they are using, and what is the throughput of your architecture and all. You will be checking, and based on that, once you get this soft DSP, you will be customizing this DSP so that it will fit into your architecture. So yeah, there is a high probability of you need to tune your. It is not that if you buy a soft IP from somewhere you can directly use it in your design, but you need to tune it for that particular soft IP to fit into it in your design. So yeah, if you buy a soft IP, 100% you need to put your hands on that code and modify it for it to fit into your original whatever architecture used. So I think I answered your question. Hello?
Yes, sir.
Did
Yes,
I answer
sir.
your question? Yeah, okay. So, um, sure, sir. So, let's get into this hard IP. So, this hard IP, you cannot alter the logic, and uh, yeah, it need to be used as raw. That is the difference between the IPs. So now let's get into what else we have. Yeah, we had the schematic and so it will be. And the logic stage, when the logic synthesis, what will happen is, so I told you, right? There will be standstill layout engineers, and they will be providing all these gates and all. So they'll be providing the area information in the form of left and timing information in the form of the lips. So while you're doing the logic synthesis in the first stage, it is called generic synthesis. So the tool will insert its own generic gates. Okay. So you might not be able to make out the area and timing with those generic gates. Let us say these gates are generic gates. Then they are dummy, like they are just for logic purpose. Okay. So in the generic synthesis stage, they're just for logic purpose. You cannot make out any timing or area for these generic gates, but there will be something called as that is called technology independent mapping, and you will get a technology independent circuit. Okay, you'll be getting a technology independent circuit when you do a technology independent mapping. So then there will be some optimizations. Okay, and they'll so before you actually map to the technology gates that we just discussed, which is provided by the TSMC or UMC or Intel foundries or any other foundries. So when the technology is mapped, then they will get the drive strengths, different attributes. They will get the timing. Okay, they'll get the area. So then you can make out what is what once the technology mapping is done. So the synthesis is done in two different stages. One is generic synthesis, that means technology independent synthesis, and another is technology dependent synthesis. So once you get the technology dependent synthesis, you write out the netlist and take it as an input to the physical design. Okay. Any doubts yet? Can I proceed?
Yes, sir. Sir. Excuse me.
Yes, sir. Yes, sir. Yes, sir.
You can
Sir,
proceed, sir.
if
You can
risk-like
proceed.
process are there,
Sorry. Sorry,
sir,
what
if
was the question, sir?
risk-like process are there, na?
Okay.
If risk-like process are there, after now let us consider this year I have written some code on the risk processor. After 5 years, maybe risk processor will update that processor. If I want to use same code
Okay.
after 5 years, can I use it?
No, you. So let us say you have written. I think there is someone raising the hands. Is it- Are they raising the hands? Okay. So okay. Many people are raising the hands. Oh, Bharadwaj is rising hand continuously. So I think there's some issue. Okay. Sure. So yeah, sir. To answer your question, let us say you have written a code for a DSP, okay, or maybe for an ISP or some video signal processor or something. So you have written in such a way that it will fit into the current risk architecture. And after 5 years, if the risk architecture will get updated, then you cannot use the same code after 5 years. You need to tune it again, such that let us say currently in the RISC architecture you have 32-bit bus. Okay, after 5 years you will get 128. What's 2 power 8? 512, right? You will get a 512-bit bus. Okay, bit. So you cannot use the same code, right? So you need to update your code. And yeah, that's how it is. Did I answer your question, sir?
Yes, sir. Yes.
Hello. So now, yeah. So yeah, so here we have seen there is an optimization stage, right, between technology independent and technology specific stages. We have an optimization stage. So in this optimization stage, what will happen? What type of optimization does the tool do? You can see related to timing. It is something like, for something to get computed, the inputs must be available in the simultaneous time frames. So when the input is not available in the simultaneous time frames, your delay will be, your width will be, consumed like this. It will not be the same. Okay, the data will be corrupted like this. So what is the width of that particular signal? You can see here, but due to this u1, and which is because of this u1, this comes a bit late and something comes a bit fast, and due to the mismatch, what will happen, that particular small portion of that phase difference where this is 0 and that is 1 will get multiplied, and it eats some portion of the 1. Okay, and we have very small, we have some corrupted data here. But here, if you add a buffer which is almost equivalent to this u1, that, if this buffer produces almost equivalent delay as that of the u1, then you will be having, you can retain your signal very well. That's how one of the timing based optimization does. And also power based optimization. Okay, so since even I forgot to tell you, the dot-lib files, there will be also the power information, the leakage power information will be there directly. The value will be given and in sometimes in a very lower technology nodes, even the power will be as in a stochastic table fashion. It's called lookup table fashion. So yeah, and in different scenarios, different type of powers can step into it. And I forgot to tell you something very important. There will be a concept of interpolation and extrapolation. Let us say we have a table, we call it as frames. So let us say this is 0, 1, 2, 3, 4, 5, 6. This is 0, 1, 2, 3, 4, 5, 6. And now we have the corresponding values like this. Okay. These are the predefined, this is a predefined table. Okay. Now you have some situation like this. Okay. And another situation like this. Now what happens? This value fell somewhere between 3 to 4. Let us say this is output cap. And this is input track. And this value fell somewhere between 3 and 4. And this value fell somewhere between 2 and 3. Okay. Then we have the delay value for exactly 2 and 3 intersection and 3 and 4 intersection. but this somewhere we don't have. So what the tool does, it interpolates, because that this question mark and this question mark is between the ranges of the maximum and minimum. Okay, if something exceeds 6, let us say, what will happen? If let us say this case, we have lots of fan out, then this exceeds this 6, then the tool will try to extrapolate. So when the tool is trying to extrapolate, it is very dangerous. It will try to impact your timing. It means the delay will be very big. Okay. So when the tool is trying to extrapolate, so that's how the things work. And so yeah. So yeah, so that's how this will work. Is there any doubts here, or can I go forward? This is a very important concept to understand regarding timing delays. I will go forward then, team.
Okay, sir.
Okay. So yeah, so in the same similar fashion, the power tables will also be there, and this tool will intelligently decide what type of gates should be used, like three fan in or 4 fan in, or you know, to reduce the power. And also similarly the area. The tool is intelligent enough. It checks the logic there, and it is intelligent enough to. It will have a lot of options. You know, it will have the same. And there will be 30 or 40 different types of end gates. You know, each will differ in the flavor of threshold voltage. Okay, it will differ in the flavor of the width of the channel. It will differ in the flavor of what else? Yeah, yeah. In fan in, and like 3 input or 2 input, like that. So there will be different types of end gates. The tool will have a lot of options, so that, and it is very aware of those options, so that it can pick the best one. Okay. So it is. So there is always a trade-off between delay and area. So if you want to reduce the delay, you need to use a lower area consuming, lower area consuming transistors, because it is simple. It is simple. If the channel width, width of the channel is lower, then what will happen? The resistance will increase and the delay will increase. If you reduce the width, the area decreases. So both are inversely proportional. I hope I made it clear. And yeah, timing closure and timing constraints. This is very important. So I'll quickly explain you STA. This is very challenging, to explain STA in just a glimpse of minutes. But yeah, I'll try. So if you come here, right? So the timing is checked between 2 consecutive flops. Okay, or pipeline stages. This here it will be clock. It's another clock. D pin and the Q pin. D pin and the Q pin. This is the combinational cloud. So whatever the data, it will be in between two flops. So the chunk, so if this is a chip and there is chunks of data, so those data will be pipelined like this. Okay. So why do the pipeline? For more performance, for the parallelism, and so these pipeline stages will have flops. So anywhere in the design, you will be checking the timing between two consecutive flops. And so this flop will launch the data. This flop will capture the data. That's what this is called launch flop. This is called capture flop. So here comes the timing. Timing. This is STA. I'm literally telling you STA in a very brief manner because we are having shortage of time. So let us say this is a clock signal that is going. This is going to the launch flop because the clock is going simultaneously, right? To both the flops. So this clock signal is going to the launch flop, and this clock signal is going to the capture flop. Let us say both are having the same time period. Let us call it as T. T. Fall edge, rise edge, fall edge, rise edge. Okay. Now, the data is being launched here. Okay. It will travel for some amount of time and it will be captured here. So this amount of time, how much time it travels or it takes to travel before this gets captured at this clock edge is very, very important. That is called TPD or propagation delay. Okay, of that particular combination of clock. Or we can also call it as T combi also. We will call it as T com. And there is also, when the clock triggers, there'll be a data here at this edge. Let us say it is some D naught. So for this D naught to come to Q, once the clock is triggered, it will take some time. That is called T clock to Q. Okay. So now, let us say the clock triggered. So first delay will be T clock to Q. It takes this much of time. Let us calculate the time in the timing graph. Let us put it in the x-axis. Let's put it in the x-axis. So it took this much of time. Sorry. It's just trouble anyway. Okay. So it took this much of time for TC to Q. And again, it took this much of time to pass through this combinational cloud. This is T combi. Okay. So we need to add these both. So once you add these both, the data is now available at the capture edge. Means the data traveled from here all along to here after this plus this of time. Okay. From this D pin, it traveled to the next flop's D pin. From the time taken for that to travel is TC2Q plus T combi. That is this much. But here we are capturing. So the violation occurs when this data time, the traveling time, when it exceeds this time period. Let us say this is traveling time is arrival time. Arrival time when it exceeds the time period means if the train is at 10 o'clock, you need to be there by 10 o'clock. Okay. If you go after 10 o'clock, then the train will depart from there and you will not be able to catch up the train. As simple as that. So the data will not be captured there. It will miss one cycle. So it might lead to functional failure, or it might lead to latency. Okay, that would be desired. That would be see, if the data is late to the capture flow, two things can happen. One can be functional failure, and one can be latency. Latency of one cycle delay. Okay, but in some cases, the functionality itself will be there. Like in this data should come by this cycle. If that will not match, then it will be a functional failure. So it is very, very important to check whether there are no violations. So now, since I hope this is clear, now I'll tell you. So this is the capture edge. This is the launch edge. This is the capture edge. So the similar way I told you, if the train is at 10 o'clock, you should be at least 5 minutes before, right? So let us say train will come at this edge. So you need to be 5 minutes before. So this is a setup time. This is called library setup time. So it is a minimum time required for the data to be stable before the capture edge. Okay, means the data to be stable is in the sense the data. See, here there will be previous data, preview data. So once this first clock is hits, right, this preview data will be going here. So, yeah. So, but still this pin will return the previous data. Anyhow, by the time the second clock is hits, this new data should come and sit in this place. Okay, it should be readily available, and it should sit in this place. So that means the data started here. The T clock to Q plus T combinational delay must be before this window. Okay, so if you take this equation will be, this is T clock and this is T setup. I'll call it as TS. So you'll minus this, right? So your window is this. So you need to minus this. So this window should always be greater than here TC2Q and T com. So you'll be putting as TC2Q plus T com. That's how it is. This is setup equation. Setup time requirement. Any doubts? I'm open for doubts for 1 or 2 minutes.
Sir, actually,
Dear
static timing analysis is already discussed in the second day, sir. You can go quickly.
Oh, is it? I don't know that. You could have interrupted me. It's okay.
Yes, sir, take a
Um,
5 minutes break. These topics are already covered in the earlier sessions.
Okay.
Okay.
So we'll take break now.
Yes, sir,
If you
take
want,
break.
you can, sir.
Oh, okay. Okay. I think I want to continue. Like, you guys want to take break?
No, sir, you
Hello.
can.
Okay. So yeah. So the setup time requirement is it? Since everything is completed, you said everything is completed, right? So you are aware with the setup time, right? And you are aware with the whole time requirement
Sir,
also.
excuse me, sir.
Yeah.
Sir,
Yeah.
excuse me, sir.
Yes.
If any time you want break, you can, sir.
Okay. Sure. I'll take a call. Yeah. I just want a clarification if somebody can give me, like, so you're aware of skew? Skew. what is Q, how
Sir,
it affects
clocks queue.
the timing. Yeah, you're aware, like, was it discussed in the ST sessions? Hello.
Yes, sir. In the yesterday's synthesis topic, madam explained about that skew,
Oh,
setup time, hold.
okay. Then
That's
then it is then it is then it's awesome. Then I think I'll stop this thing here. I'll go deep into the things, and if you are stuck somewhere, you can just step in and stop me. Okay. So the timing constraints. So you're aware of SDC, or do I need to discuss SDC? SDC.
What is
Hello.
your full form, sir?
Synopsis design constraints.
no, sir, not it.
Not yet discussed. What about these different path types? What these discussed? Into reg to reg, reg to out. Yesterday.
Mm.
Okay. Anyhow.
The paths are discussed, sir. Just paths.
Okay. Okay. I'll just give you a small brief here. So yesterday you might have discussed about into reg to reg, reg to out, and in to out. So basically, what will happen is this. Okay. Okay. So you will have a flat netlist. Okay, a flat netlist, and you will divide that flat netlist into different sub netlists. Okay, for parallelly working. For the parallelism in the work, and to reduce the burden on the compute resources, you will be dividing it into different blocks. So let us say this is your block. Okay, so if you are handling a block, you will be only having the idea of your block and what and all the instances and the macros involved only in your block. You will not have any idea outside your block. But ultimately, all the blocks comes under the same chip, and the full chip designer will be having idea of all the blocks, and he can access all the elements in all the blocks. But if you're a block owner, then you need to you need to so you have only limited access until your block. So let us say you have a register in your block, and this register is communicating with some other register in some other block. Okay, so then for you, this particular interface point will be the output port. Okay, and this will be a reg to out path. Okay, so I'll be discussing about STC, and you will understand better. And similarly, for this guy, let us say this is block A and this is block B. For this guy, this will be a into reg path, because this signal is coming like this, and this is an input port. Okay, this will be an into reg path. And let us say there is another register here, and there is another register here. So the best way to propagate to connect these two is taking this register through this block to this flock, shortest distance, right? So then these are called feed through ports. Okay, I'm just extending the topic yesterday's feed through ports. These nets will have nothing to do with any functionalities in this block. They'll just pass through this block, and they'll reach out to this particular flock. Okay, so you need to internally, what you need to do, let us say this block is having module input 1, input 2, output 1, output 2. Okay, initially. So you want to, in physical design, you have seen some issue here, like you want to propagate this particular signal through this block. So what you will do, you will try to create dummy ports. Let us say that is a feed through ports, FE1, FE2. This FE1 will be input port, FE2 will be output port. Understood? I think things are being understandable. This will be output port. Okay, team. So now, what will happen is, since we have written two ports, this port should not be dummy. Okay. You need to define some wire. The wire will be FE, feed through wire. And this wire will be connected to the input port, and it will also be connected to the output port. So you should not connect directly. A single wire should not go like this directly. This should be buffered. Okay. I already told you the reason why it should be buffered, to reduce the transition time. If you don't buffer right, what will happen? The 0 to 1 transition will be very, very big. So if you want a quick transition, you need to buffer. So this should be buffered. So you will add some buffer instances, and you will be connecting that. Maybe you can call it as G1 buff. Maybe you can call it as S. This is buffer will have some input I, and the Y will in the I will be the CD wire, and then it will have an output Y. And this will again go to the G2 buff. Like that, let us say we have only two buffers. And then it will go to the output port. Maybe you will put this S sign Y, maybe output port FE2 to this value, I think you can call it as. You can take this wire here. On one more wire you can declare, and that wire output you can assign it to this particular buffer, and you can assign it here. I think I'm not that good with front end, but I think it will be something like this. So you need to create some extra ports in this module and this. So this particular path is also a timing path. Okay, this will be into out. So yeah, this is what I wanted to discuss. So I think I'm clear with this. Okay, I'll go forward. So now, what I should discuss is, what I mean, parts is done, and
Yes, sir.
yeah. Okay, all this is done. Static timing analysis already explained. Okay. Now let us come to PD. Exactly, we are halfway. So all the introduction is done. So we started at 6. It's 1.5 hours almost. Now let us. This I think this is an interval. I mean, we didn't take an interval, but this is in. Post interval session of the movie. So yeah. So now we have done synthesis, and we are having, let us assume we are having the netlist. What is the output? The output of synthesis will be the netlist. And also we can write out SDC from synthesis. So these two will be the outputs of the synthesis. Anyhow, we have the dot lib and the dotless, dot and the tech dotless. All this will be having as an input anyhow. So these will come from the netlist specific. These will come from synthesis specific. So now I would like to discuss the input files. So now you guys knows what is a netlist. Okay. So now here we have a very good presentation from here. So the netlist is basically a combination of the stencils and instances. The connections will be there, and you have an example. So now I would like to talk about the fan itself, how it will be there. So it will be something like this. If it is a buffer, right? If it is an AND gate, right? And 2 D D D4 HVT. Okay. So this is a sort of IUPAC name. It might vary from one version of the dotlet to another version, or it might vary amongst the foundries. This will be the fan. How much? It's 2 input AND gate. This is the drive strength. This is the threshold flavor, VTH flavor. So we all know for MOSFETs we have 2 conditions like VGS less than VTH. This is off, and VGS minus VTH greater than I think VGS greater than VTH, or this you can call it as greater than 0, and VDS is greater than equal to VGS minus VTH. This will come as a on or saturation. So this VTH, what we have, VTH, we have 3 flavors. One is LVT, SVT. Also, we have ULVT also, and not everywhere, HVT. Okay. Here also we have another classification, LL, and you will have something like let us call them as prefix. Then we can call them as, and we have these also, pref LL. Okay. So if you have ULVT, then you will also have ULVT LL. If you have LVT, you will also have LVT LL. If you have SVT, you will also have SVT LL and HVT LL. So why do we have these many flavors? So one simple question, it's a generic question, like you can basically try to answer it. If we have lower VTH, then what will be the delay of the MOSFET? Simple question, like you can participate in this. Lower VTH will rise to higher delay or lower delay in the MOSFET.
Lower delay.
Correct. Lower VTH will always give you a lower delay because the channel will be very fastly formed, and the current will flows very quick. That's a correct answer. But what about, is there any disadvantage of lower VTH that you can find? It's very
Power
tricky.
consumption.
Exactly,
Leakage, sir.
exactly. So if you use a lower VTH, then there will be leakage. So how will the leakage occur? The electrons should flow from source to drain, but what happens when there is a leakage? it will try to penetrate through the substrate because it is also connected to the ground terminal. That will be the leakage here. So the electrons that are to be involved in the source to drain stuff can sometimes go sideways. So in the lower VTH. So ULVT is ultra lower VTH. That's very, very low VTH. Okay. So if you take this, okay, the delay trend will be increasing. So let us take this. This is ULVT. This is LVT. This is SVT. This is HVT. The delay will increase. The delay will increase. Okay. If you take same, yeah, I'll take it here only. Okay. I'll take it here only. Maybe I'll use some red one this time. If you take power will decrease. This is a trade-off. So you need to check the trade-off and you need to fix what type of VTH you will be using. So what is the drive strength? What is drive strength? You guys, are you aware of drive strength? Is it discussed in the previous session? Can someone let me know? Drive strength. Do I need to discuss, or is it already discussed in the previous session?
No, sir. No, sir. No, sir.
Okay. Okay. Thank you, ma'am. So the drive strength is nothing but the strength of the standard cell to drive the signal. Okay. Let us say this is a buffer and this is another buffer. So this is called as driver cell. Okay. Driver cell. And this will drive. That's why it's called as driver. And if this has another cell behind it, and this is driver cell or load. Sorry. No. This is the driver cell. Okay. So sorry. This is driver cell. And this is the load. This is load. So this should drive this signal to this so that it will have a very small transition time before it it reaches the load. So what happens sometimes is that you will have a very big cell here and a very small cell here. Okay, so I think things have been understood now. So now let us say this is a signal S1. So this signal will be driven by this cell to this load. Okay, it should come like this and should pass through this cell to reach this load or charge this load. So now what happens if let me ask you a quick question. So who do you think the drive strength of A is more or drive strength of B is more? Simple question. Drive strength is nothing but the size. More the drive strength, more the size, right? So drive strength of B is more, obviously. So if the drive strength of B is more, that means its size is big. That means its width is big. Okay. So the drive strength, so the width, this has a more width, and this. So if the width increases, what about the capacitance of the dielectric?
Increases, sir.
Exactly. So epsilon A by D. So width increases, area increases, distance is nothing but the distance between the two plates, but the dielectric. But as the area increases, the capacitance increases. As the capacitance increases, the load value increases. And as the this is the output cap, right? This will be the output cap to calculate the delay of the signal for this cell. Okay. So if the output cap is high, we just saw it, a table. What will happen? This is my maximum. Let us say we got a maximum value for this particular load. Then what will happen? Extrapolation will happen, and my delay will be very, very big. Okay. So what should I do? I need to upsize this cell. Yeah, I need to swap this cell, which has same functionality, but with higher drive strength. So I need to make it bigger. This is how it works. Okay. We need to play with drive strengths in fixing the timing issues. Okay. Similarly, this is the IUPAC of the standard cell. I just wanted to discuss history of the standard cell. Similarly, sometimes if you want to reduce the delay, you'll have the same conventions. Okay, you'll have the same convention, but you'll just change here. You'll be able to change, like you'll be able to swap one cell from other cell readily with the same convention till here, and ULVT will be available. It will be readily available in the dot level. Okay, so we can just swap it whenever required. Okay, so that's how things work with standard cells. I think I'm clear, right? Team? Any doubts?
Yes, sir.
Yeah. Okay. Okay. So that's what about the drive strength and the VT flare. So we go. Yeah. So now I would like to discuss about synopsis design constraints. Okay. So basically, synopsis design constraints will have clock definition. Clock is the most important signal in the design. We define clock, and while defining clock, we define something called as period, the name, and the clock will not simply be defined. It has to be defined on some port. It's called clock port. We get clock from outside. From where do we get the clock? We get it from PLL. What is PLL? It is phase lock clock. So we need to define a clock on a port. So then we need to define on which port we are trying to define the clock, and what else? We define the duty cycle of the clock. The clock definition will be there. What else will be there in the SDC? We have timing exceptions. Okay. So we have something called as modes and PVT corners. That's very, very important. Okay. Let me explain you the input files first. Timing exception is nothing but, let us say we have a mux, and we are giving clock signal CLK1 and CLK2. So in one mode, so we have something called as modes. Okay, we'll discuss. So in one mode, we are using clock 1. In another mode, we are using clock 2. So which mode we want to use, we'll decide it by the select line. And let us say we are using constant signal S equal to 0. That means clock 2 is going and all the circuits. So all the timing arcs which involve this are dummy. If you can, like, if you report the timing in the design, you might get violations that include this timing arc. Okay, so they are all dummy violations. So you need to set it as false path. Okay, so there will be different categories also in this false path. I would not want to go into deep of it, because the next whole session will complete with the same concept. That's why let us move on. So this is one exception, and there is also multi-cycle path. There's also something called as multi-cycle path. Okay, the multi-cycle path is something that will actually, um, you'll be able to use it when your delay is very, very, very big than the clock period. In this case, you will say to the tool that do not check the setup time in the first clock edge, but check the setup time at second clock edge. So that if your delay exceeds till here, then it will be fine, right? If it checks at second clock edge. So this is called, these are the timing exceptions. These will be there in the SDC. And I already told you, right? What did I tell you? That this is a block and there will be some register. This register will communicate with some other register in some other block. So I will have a port. Okay. On this port, I will actually have to set some delay so that I can assume what is that, what should be the delay. See, if I'm a block owner of this block, then I will not have any idea about the delay here. I will only have idea about delays here in this perimeter, but not here. So what will the top level guy do? He will go for flat ST errands and he will calculate the delay here and he will give us, he will update our SDCs, and we need to set the delays by what he has given us. And that particular process is called timing budgeting. Okay, it's called as timing budgeting. So, so that particular delays will be. Hello, sorry team, I just got disconnected. Am I audible now?
Yes, sir. Yes, sir. You are audible.
Till where was I exactly when I got disconnected? Can someone help?
Timing budgeting, sir.
Oh, okay. So that is okay, fine. That is called timing budgeting, and so you will be able to calculate the delay here. Someone who is doing a flat STRs will be able to calculate the delay here, and
Sir,
you'll be.
your presentation is not visible.
Okay, okay. I will initiate the presentation. Just a second. I think now it is fine.
Yes, sir.
Okay, okay. Sure. So, yeah. So I'll get these delays. So these are called asserted delays, and I'll get this on this port. Now my tool will be able to calculate it as an edge to out path, and it will have the delay of here also here. But now I'm asking a question that how will the tool know on which clock edge I need to check? Because the capture flop is not inside my block. The capture flop is somewhere outside. So how will the tool know that? Like, you don't need to answer the question, but I think, am I clear with my question at least, so that I'll answer in a better way? You all understood my question?
Yes, sir.
So I don't have the capture flop in my design. So it is somewhere outside. So I don't know what clock is going there. Even if I know what clock is going there, how can I simulate that in my design, in my block? So I can do that by the concept of virtual clock. So this virtual clock, I will define this virtual clock. So in the SDC, if you find some create clock, this is create clock definition. This is the command exactly to create the clock. So if you do not use this switch or this particular argument port in this particular create clock definition, then it is a virtual clock. You can blindly go there. And this clock you will be using when you try to set input delays and output delays, especially output delays. Set output delay will also be there similarly. Okay. And if you mention if you mention this clock and you will define it as on a port, like the delay will be defined on the port, and you will also mention this virtual clock so that the tool will check with respect to this clock edge. I think I'm clear. So you need to provide information to the tool of the unknowns. So that's how it will work. So these are called these are all called timing constraints. And also, while the tool is optimizing something, it might exceed in some aspects. That is transition and capacitance and delay. So you will be able to, you will have to set maximum delay. You will give constraint like please do not cross this particular value while you're optimizing. Do not try to cross. Tool can cross. That is called DRV violation, design rule violation. So you have defined something called as max strand. You give using set max strand. You have given some value of some 0.3, but the tool exceeded to 0.4. Then your DRV violation will be minus 0.1. You need to fix it. Sometimes you need not address it also because this is not a violation. This is a precaution. That means you are giving tool as a precaution. If you exceed this value, then definitely somewhere the timing will degrade. So that's how you are, cautiously telling the tool using SDC. Do not optimize in such a way that this max stand value might increase to 0.3. Okay. So because
Sir,
optimization, yeah,
okay, sir.
yeah,
Sir,
yeah.
is it to explain any one example on Synopsys tool, sir?
Sorry, can you
One,
come?
then it is easy for us to understand.
Oh, you're asking to explain it,
If
it
it
on
is
the tool.
possible, if it is
No, no,
possible, then
currently it is not possible, I think. Yeah. Like
okay, sir.
showcasing the tool is not possible currently. I
Okay,
think
sir.
You may check on some other time.
Okay,
So
sir. Thank you.
yeah, no problem. So just give me a moment. So thing is, yeah, this is what SDC involves. Okay, so okay, you can see here there will be optimization directives. Just now I told you about max time, max cap, and max limit. They are the optimization constraints, and remaining are normal constraints, the clock definitions, the timing exceptions. You can see. And this is a Liberty file, .lib file we already discussed. So this is the name of the cell. And this is a basic .lib. We don't have that UL with that advanced stuff here. And you will have the area of that cell. Okay, that's how you calculate the area. Remember this. We'll have to discuss this on again another moment of calculating the utilization and all that. So you will have the delays with respect to pins. Okay, the timing tables also you'll have with respect to pins. No. So basically, the dot lips are in the form of NLDM and CCS. These are the two different formats of. This is this is single dimension. This is 2 dimension. This is 3 dimension. Single dimension in the sense the RC, RC delays, and NLDM is nonlinear delay modeling. It is of 2 dimension. That is input run and output cap. CCS is composite current source. That is something related to you will have input RAM, you will have output cap, and you'll have the charge variation also with respect to time as a third dimensional axis. Okay. So on the fourth dimension, you will get the plot of the output. I mean, the delay will be function of f of x1, x2, x3 in CCS. So it is very, very accurate, but CCS will take a lot of time to load the design. So yeah. So I think I'll discuss about MMMC corners in a while. And yeah, this is LEF. This is how this looks. We'll have a size. It gives basically the abstract shape and size of the design. The pins and the pin locations, obstructions and blockages. I'll discuss about obstructions and blockages. This is a technology file. In the tech I have to discuss. You'll be having the information about how many metal layers you are using. So we don't connect planar. Okay, our interconnects are 3 dimensional, and we use orthogonal 3 dimensional interconnect or metal stack interconnect models. So we need to have when we use them, we need to have the information about the pitch. We need to have the information about the width, thickness, resistance, maximum current density that can pass through a particular wire. All this information we'll be having in the technology file. Interconnect parasitic file. So you will have to connect it with metal layers, right? Metal, right? It may be gold, copper, aluminum, or silver. So it will have different metal layers. Will have different widths and all. So the interconnect capacitance values will be there. So the delays of the nets are calculated or based out of RC values. So this particular file will contain those values. This is an advanced RC parasitic file. TLU modeling. It will require separate RC extraction tool licenses for you need to pop in this particular information in your design. And we have IO information file. So we'll discuss about that while doing the floor planning. And power specification file. This is something about low power, which we'll not be covering in this session because it is again a huge, very, very huge topic. So maybe we can make a progressive. We can take the progress maybe in the future, but currently we'll skip that topic. Optimization directives. So we will be having don't touch and don't use attributes where you will be basically you have a bunch of cells, but you want to use only some cells. You don't want the design to use some other cells. So you will just have to put it in the don't use list, so that while the tool is doing some optimizations, or tool will add buffers in the physical design during optimizations. So while doing that, it will not touch those cells or use those cells. Or if you are having some already existing cells in your design, and if you want the tool not to optimize them or not to touch them, you will put it in the don't touch list. These two are two unique attributes you'll find. So this is how you need to import the design. You need to collect all these input files and you need to, and there'll be, in Innova's tool, there'll be init global variables, pickle variables. So you need to define them, and you need to give a small command called init_design. So it will create you a design environment with all these binded together. So you can start your design after initializing it. So now before going to the floor plan, we will have to do some sanity checks. The sanity checks will be done before
Excuse me, sir. Excuse me, sir.
Yeah.
I have a doubt in the previous slide.
Yes.
In slide 42. Sir, here you mentioned the point related to core area. So how can we define this core area? Do we have any kind of mechanism, sir, to define the core area?
Yeah. It is very visible actually. Like we have already discussed here. If we could rewind our session, we have already discussed here that in the synthesis, in the synthesis, we involved left. Am I right?
Yes, sir.
So what does this left? And we also involved lib.
Yes, sir.
So what does this left or lib contain? Does it contain the area information of the cell? Yes.
Yes, sir.
Does it? Yeah.
Timing
So how does it? Yeah. So how does it contain the area information of the cell? I have shown you.
Yes,
Here,
sir.
yeah. So here we have this liberty timing file, and here you have something called as area equal to some value, right? So now, once you do the technology mapping, right? So your netlist, let us say your netlist, in your netlist you have something like this. Only this you have in another. Let us say this is the chip you're designing, for instance. So you will have this area, you will have this area, you will have this area, this area, this area. So A1, A2, A3, A4, A5. If you're using some ROM and you're reading or you're writing or something like that, you're reading from this ROM and you're writing into the ROM by processing it. Let us say. Let us be somewhat creative while we're discussing things. So now you need to, you will also have as area of the ROM or RAM. You will add all this. The tool will add all this, and it will give you the total standard cell area. And you can get this in the synthesis stage itself.
Suppose if I want to optimize the area parameter, so in the PPA, if I want to optimize area parameter, then what care I need to take, sir?
Okay.
Regarding core utilization.
Okay. So firstly, I would like to tell you that before optimizing the area, like you will have to come to a point where you need to feel to optimize the area. Okay. See, until unless so the things how it goes in the physical design is there will be a spec, right?
Yes, sir.
In this spec, you will have this much should be the area of your chip, because the PCB is already there, the board is already there, and this much should be the area of the chip. This will be in the spec. So now, what you have in your hand is the total standard cell area. Okay, so this total standard cell area you will be having, and first you need to go with the utilization. Utilization is something that will come here. Utilization is nothing but total standard cell area plus macro area plus hard blockage by length into width of your design dimensions. If it is a rectangle, it's a rectangle, or if it is a polygon, you need to calculate the area of the polygon. So this will give you the utilization. So initially PD engineers will go with a sophisticated utilization percentage, that is 65%. Okay, they will go from floor plan to route with this 65%. Okay, ma'am. So
Understood, sir.
So if the design results are good, are converging very easily, then they will increase this utilization. So if they are increasing this utilization, what they are doing? Let us say they increase this utilization to 85%. Because at 65%, design was meeting very easily. The turnaround time is very slow, very small. And they increased to 85%. What made them increase to 85%?
They might be giving more area to standard cells.
More area to standard cells or less area to standard cells?
85% utilization in the sense most of the area must be utilized, no, sir?
Exactly. The standard cells areas cannot be touched. It can be swapped, but that's not the way to increase the utilization. Utilization can only be increased manually by changing these dimensions.
Okay, so the dimensions are being shrinked.
Exactly. So if your design is being converged very easily in 5x5, then why not converge your design in 3x3? Your area got reduced, right?
Yes, sir.
So this is one sort of area optimization where you are shrinking the whole area. Okay.
Okay,
So this is one sort of area optimization. Another sort of area optimization is, let us say you can't shrink it anymore because you have a PCB. The PCB guys will do some iterations over this area and they will fix one final area. And now you can't shrink it anymore. Now, if you can't shrink it anymore and you are getting lots and lots of violations because of these standard cells, then you need to reduce the area of the standard cells. How you can't reduce it manually, but you need to control the tool such that it will not add higher drive strength cells while optimizing the design for timing or power. If higher drive strength cells are added, it will take more area compared to a less drive strength cells. And yeah, that's how you do the next sort of area optimization. These are the two different area optimizations you do. And the question you asked was how to fix the core utilization. The fixation of the core utilization percentage will be an iterative process where you will start from a low util and you'll go to high util. And if your design converges here and the dimensions gets fixed, then you will continue with this to your final runs. Yeah.
It's a pure trial and error based, sir.
Exactly. Yeah.
Understood, sir. Thank you, sir.
Okay. Thank you, ma'am. That was a very good question. And yeah, and now let's go a bit deep. So partitioning. Now let's start the PD, actual PD. The partitioning is something like, see, currently we are having the designs which have millions of gates, millions. Millions means easily the design which calls 10 lakhs. So 10 lakhs of gates. So if it is crossing 10 lakhs of gates, average transistor count per gate, if you take it as 5, then it would be 5 into 10 lakhs. The transistor count will be 5 times, on an average of the gate count. So this is a very, very huge compaction, or I don't know what word to use, but you're literally compacting the things into a very, very small area. So what happens is, see, when your design is having such a huge gate count, it is a very, very big burden to the tool. For example, I'll tell you, placement is one stage in the physical design, which can run up to 8 hours for 8 days. Sorry, 8 days. It will literally run 8 days. If you hit an enter, if you just hit an enter for the whole process to come out, the Linux shell will be completely occupied by the process. You cannot access the Linux shell. The whole process, of course, you can throw it in the background jobs and many things. You can do many things in the Linux, but in a layman fashion, the whole shell will get struck for 8 literal days, and after 8 days, you'll be getting the output. The shell will again up. Okay, it will come up in the foreground. So 8 days, it'll at least take for 10 to 15 million instances. This is the placement. CTS can take 6 days. Route can take 10 days. To go for a flow flush from placement to route, to go for a flow flush, it will easily take 20 days and consume more than 60% of 1 month duration. If you go for a flat PNR of 10 to 15 million instances. So what is this flat PNR of 10 to 15 million instances? It is nothing but the netlist will contain the 10 to 50 million gates. So you need to break down the netlist into parts and give this netlist to one guy, this netlist to another guy, this to some other guy, this to some other guy, call them as block owners. And then they will be parallelly doing the PNR, and then finally they will integrate. Individual boxes will be integrated again, finally. So what will happen? That this 10 million reduced to, let us say, 2 million, 2 point some million, 2 point something, 2 point something, 2 point something. So these 8 days will be reduced to maybe 3 days or 2 days. So in 2 days, this guy will come up with his block design. In the same 2 days, if he hits parallelly, he comes up with a design, he comes up with a design, he comes up with a design. And in 2 days, the 4 guys will came up with the 4 solid blocks, defs. So you need to merge everything and you need to go for a flat. So this flat will have some glue logic intermediary, and the top level guy will be taking the inputs of this block level Verilog, block level spec, block level defs, and these are also called as ILMs. Okay. So this block level ILMs will be taking. He need not do anything for this, any PNR for these blocks individual. They're already done in the 2 days. He just need to integrate it. That's it. So the integration will take some cost around 4 days, 4 or 5 days maybe, because the internal glue logic will be very low, and these are already, hardened. So the overall integration, the full chip level integration will take just 7 days. Just I'm giving an example, 6 to 7 days. Here you can see it took 20 days, right? So that is the necessity of partitioning. I hope I'm clear. The netlist will be broken down in partitioning, and the netlist they will take it as an input, and each person will be importing them and will parallelly working on it. I hope I'm clear. This is how the block A will be partitioned, the block B, block C, block B. Right? And parallelly, they will be working. Once they are hardened, the top level guy will try to integrate. The blue is nothing but glue level logic. So again, if you create a block separately, you need to create an SDC for that. You need to create. That is also very tedious. So you cannot. If you have 10 blocks, you need to have 10 engineers, and you need to pay 10 engineers. Right? So that will be very tedious for some company. So it is a trade-off, however. So the floor planning. So now floor plan is nothing but we need to allocate some area for the chip, and it's obviously either a rectangle or a polygon. That's for sure. And then we'll have macros. Okay, we'll have hardened macros. I have told about hard IPs, which are already hardened, and we'll buy from them. Similarly, we'll have hard IP, hard macros for the memories and all, and we'll be placing them previously. Here we have blocks. Blocks can be, you just try to treat this as a hard IP or memory. So memory we will be placing in this fashion. First is abutted fashion, the next is non-abutted fashion, third is mixed fashion. Abutment is in the sense we'll not put any gap between the blocks, and we'll just abut them like this. Non-abutted will have the gaps, but we can abut them with the edges of the core. Mixed, we can have the both type. It's based on us. So we need to use our common sense, and we need to try to come up with a very, very better floor plan. So basically in industry, engineers will try to come up with 3 or 4 floor plans. One will they'll go for the full flow flush of all the 3 floor plans, and one will come into the shine, and they will continue from there onwards. So basically, this is how you define the utilization. I just told you. And if you have a top level full chip, you will have die boundaries and core boundaries separately. Between the die boundary and core boundary, you will have the IO pads. The IO pads will be interacting with the other signals, other environment signals. And in the core area, you will have the standstills and macros. Okay. Horizontal and vertical routing resources. So I need to tell you that the routing resources are 3-dimensional. Okay. This one I think I need to tell you a bit, so that next slides will be very, very easy. So let us say this is your chip. This is your chip. And let us say this is a point and this is another point, and you want to reach from this point to this point. So you will have to only travel orthogonally, and you can travel top also. This will be a via. Okay, and you travel metal 1, and then I'll change the color. You have hit another. You need to go 1 unit in the Z direction to go to another metal. Another metal will be only in horizontal, not in vertical. If your bottom metal layer is vertical, another metal layer will be in horizontal direction. Horizontal, vertical, that will be the orientation of the metal resources. And while you go from the bottom to top, the width of the metal resources will increase. So the resistance will decrease going from bottom to top. That's why the power and everything are robustly built on top metal layers. The power mesh will be built in on the top metal layers so that the resistance will decrease and IR drop is very, very less. So for to go from here to here, I need to travel like this. And again, if I need to, I'll change the layer. And again, I will come like this. And again, then I'll try to again come down. I'll come down and I'll go like this. Sorry, I'll have to use the red. Have to use the red and then again come down and go like this. This is how I route. So I use the three-dimensional space to route, and as I said, the first metal layer will be here, like this, horizontal. The second metal layer will be maybe this is vertical, and this will be horizontal in some height above this first metal layer. And the next metal layer will be again vertical. Okay. So these, what I'm drawing, these are called tracks. So tracks will be like the central axis lines of the metal layer like this. Okay. So we will be having limited amount of tracks and the metal will be routed. The metal will exist where the track exists. So if we use all the tracks, so we need to be very, very careful. This is called congestion. We'll discuss. So we need to be very, very resourceful while doing the design. If we use all the tracks and if there are any other standard cells that are need to be routed, we cannot route them because there are no availability of tracks. So then the design will come into shorts. Give me a moment. So I hope things are clear to here.
Sir, the track dimensions are uniform, sir, in all the metal layers, or they may
need not be uniform. Like the distance between the two tracks need not be uniform. We can also customize the tracks. We can create non-uniform tracks. There are commands for that in the design.
Okay, sir. Understood.
Yeah. Okay, Ram. So yeah. So now we come back to the PPT. So we need to be very resourceful. So the aspect ratio will be the horizontal by the vertical dimensions, and next we have the utilization. See, if we have more area, in the first slide we were able to find the cell more dispersed. In the second slide, we have more cells in the same area. This is high utilization, and this is low utilization. IO placement. So we need to be able to, we have IO pads also. These IO pads is something, they are analog macros. IO pads are nothing but analog macros. So those analog IPs, those are built by analog guys. So they also come as separate. They will also have separate input files. They will also have separate lifts like macro lifts, and we need to place them in a certain way based on IO guidelines that will be received by the architect. And similarly, a block has ports and the full chip has IOs. I think I'm clear. And the floor plan, you first do the macro the pin placement, and then by using the guidelines will be given how to place the pins around your block. And then you will do the macro placement that we have seen previously. And then you will add some blockages. Blockages are nothing but they will allow, you have two types of blockages. One is hard blockage, one is soft blockage. And in case of hard blockage, the cells will not come and fall in that particular area where you mentioned that blockage. In case of soft blockage, some cells might come and fall there. You can control the percentage of cells that need to be in a particular area. All these sort of things you can do in the floor plan. This is a macro placement. You can see a problematic macro placement and efficient macro placement. The more the number of crisscrosses, more the number of congestion, and more the number of shots that you need to avoid. The fly lanes will be there when you have the tool. If you click on that particular standard cells, then it will show all the connections there. Those are called fly lanes. And you have halos to the macros around the macro. The halo will be able to control the standard cells not falling very close to the macros. Okay. And yeah, there are some tips to the macro placement. You can refer the PPT later about the tips. You need to always be aware of avoiding unnecessary gaps and always place the macros to the ports near to their communication. If the macro is communicating, see, these are the ports. If these macros are communicating with these ports, then place them a bit closer to them. Or if you place these macros here, then there will be long routes like this. So you need to avoid them, basically. This is a halo I was talking about, or keep out. This will be like a fence, like it will avoid other cells to come and sit here. And if you have to qualify a floor plan, there will be floor plan checks. In the floor plan checks, your macro should not be out of the core area, and there should be no macro intersections or overlappings, sort of. Yeah. And yeah, this is the power plan. So you will take the top two. You can see the three-dimensional view here, top view. Top two metal layers you can take, and you can because they have the least resistance and less IR drop will be there. So you can plan a mesh-like structure, and the wires will drop. The stacked power wires will drop and to the S rods. I'll talk about the S rods later. So these are the pad pins. The power you will get from external power supply to the pad, and from the pad to the rings, and from the ring to the stripes. These are called stripes. And finally, from stripes, they will go to rails. Rails will be in metal one, the bottommost metal layer, and in between the rails, standard cells will sit. So there will be two types of powers: dynamic power and static power. So that's quite common in any VLSI. So yeah, so it is. Extra, there will be some extra information in this PPT. So you will get the PPT, and maybe we can plan in such a way that you'll get the PPT. You can find more information there. I'll try to deliver what's most important since we are running short of time. So yeah, power planning is done, and after in this power planning, you'll have many options, like how many stripes you want to have. What should be the distance between the stripe to stripe? All these sort of options you'll have. You can mention them, and you can literally go for the power plan. So yeah, if you want, you can also create a block rings specific to the block. If the block, in the sense I'm talking about the macro. The macro is power hungry, then you can create a robust mesh here. It's all about robustness. Like, if you have more number of stripes, you're using more routing resources, and you're reducing them for the signals. So it's a trade-off. If your design is very power hungry, then create more number of stripes. It will be robust. Static power consumption is basically due to the leakage. The dynamic power consumption is due to the short circuit current and the charging and discharging of the transistor level load capacities. So VD to VSS, when both are in the saturation, there will be a short circuit current. That for a very small amount of time, so that will be dynamic power. That will add on to dynamic power consumption, and also the dissipation of this capacitor. there will be some pre-place. Now floor planning is done, power planning is done. So there will be some pre-placement cell that you need to add, that is called well taps, end caps, and spare cells and decaps. Well tap cells are used for reducing the latch-up effect. Latch-up effect is nothing but our CMOS is nothing but a PNP or NPN transistor. So what happens is like there will be a feedback connection between the two amplifiers, PNP amplifier and again NPN amplifier. It seems like that. I can tell you I think it will take a lot of time to complete this, but yeah, I'll try to explain my best. So this is your CMOS. This is N-well, this is N-well, and this is P substrate. So this is this is NMOS, and this again PMOS, I think. So this is P-well, and then substrate. This PMOS, N-well, and P substrate is NMOS. So this is completely a CMOS. Okay, you will not have any gaps while fabricating. You'll just have some sort of bias sort of things. You'll just have some separations. That's it. So you have something like a PNP transistor here, something like an NPN transistor here, and then you'll be having a feedback loop here. And once there is a small fluctuation here, then that fluctuation might feedback again to here this transistor, and it might amplify the signal again, and that amplified signal will again go as an input to this. There will be a sort of feedback mechanism that will ultimately deteriorate your MOSFET by over amplifying that small noise fluctuation. So to reduce that, you will bypass this ground with another low resistive path called well tap. Okay, so that will try to bypass that amplification thing. I just told you in normal fashion, and you can also find it in anywhere. Unfortunately, it missed the latch-up effect. It's another topic. It takes a lot of time. I just gave a glimpse of the well tap. And guards will prevent your design to exceed the boundaries of the substrates. And spare cells are nothing but in future, if you want to do any functional issues or if you want to change the logic, you'll be having spare cells. You will not touch the base. You will just route from the top by using those cells. So that's how it is. For example, if you want to inculcate an AND logic at the post-route stage, so what you just try to route through it or over it. So of course, your netlist get updated at every stage. That is also one thing. And once you place, it will be like this. The cells will place in between the rails. So these horizontal stripes are there, no? So these stripes are nothing but the metal rails, standstill rails. And from the top, the wires will drop onto these rails, where the metal one will be there on these horizontal lines, and these will power up. And the standard cells will fall on this, and the standard cells VDD and VSS pins will be in such a way that they will follow these rails. That's why these rails are also called as follow pins. The ultimate goals of placement is, you need to minimize the congestion, you need to minimize the timing, whatnot. So this is a detailed placement, and this is the course placement, and this is the legal placement. Course placement in the sense the tool will place the design in two stages. One is course placement. It will just try to place based on which cell is near to which cell is getting connected to which cell, like that. But after that, again, it tries to legalize, like the overlaps and all those stuff will be legalized. There should not be any overlaps. That's the ultimate goal. Okay. So I think I'm clear up to here. Hello.
Yes, sir.
Yes, sir, you are clear.
Okay. So in placement also there will be different optimizations. When there is a lot of fan out, right? This much big fan out results in a lot of capacitance, and hence they'll try to split the fan out by using two different cells. This is called cloning. This is very rarely done. And again, resizing. You can resize. See, if you upsize this, it can drive more number of, it can drive greater loads. Okay, the higher the drive strength, it can drive greater the fan out. For a high drive strength cell, it can have more fan out. For a low drive strength cell, it should have less fan out. So if you keep on discussing things, it'll just take a day or two to complete each and every topic in detail. But yeah, and even buffering also try to reduce the fan out. It will try to split the fan out. Okay, and you can redesign the fan in tree. Yeah, all these are there, and this is also a very efficient way to reduce the delay. You can swap the commutative pins like based on the necessity, because A into B, B into C into A is nothing but B into A into C, right? Commutative, something like that. And if you want to, there will be placement checks also. There should be no overlaps, and there should be no unplaced cells. All the cells need to be placed and getting right. So there should be minimal timing, like the 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 connected cells, the cells that have interconnection between each other should be closely placed, and during the placement itself, there will be a global routing engine. It will try to estimate the routing resources, and it will give us the congestion values. So we can get the congestion values in the placement stage itself. It will show. It is also something like a precaution. If you have more congestion, then it is, it will give you more number of shots and DSs, sort of. CDS, clock tree synthesis. The clock is a very, very important signal in physical design. It is the most. It should be very, very secure. Like it should have a Z category security, because the data launch and data capture should be very, very precise. So that's why it will be if there are other routes, if there are other signals which are going beside clock, then they will get affected by clock, because generally clock nets are very, very bigger in width, like it will be in double or triple widths. Okay, why it is bigger in width? Because the signal integrity should be very good. Like there should not be any signal loss. To sustain the loss, they will increase the width of the metal layers, especially for clock nets. So because they increase the width, there will be a lot of current density, and due to the high current density, during the 0 to 1 or 1 to 0 transitions, it might affect the nearby signals, right? The electromagnetic effect will be there. Like if there is a 0 to 1 transition, the electrons will be in one direction, 1 to 0 in other direction. The sudden surge of the electrons will create an impact on the nearby signals. Okay, so that's why there will be shielding. Shielding will be using the ground nets. The ground nets will nullify the effect and will isolate the clock signal. I hope I'm clear. I just spoke about the CTS nets and clock tree synthesis. You can. This is very, very simple to understand. We're looking at this particular slide, where see, you can find different flops in a single port. there will be some thousands and lakhs of sequentials which will be, which requires only this clock. So it is nothing. It is nothing more than 1,000 fan out for that particular port. It is feasible in the code or in the netlist, but if in hardware, it is never feasible. 1,000 fan out means the transistors will not switch, because simple, it is the junction law. If a particular current density I is entering here, then it will go as I by 4, I by 4, I by 4, I by 4. Only it will work if the I by 4 is enough to switch the transistor inside that particular gate. If the I by 4 is not sufficient, then the transistors will not switch. So we need to split the fan out, and we need to, make a tree like this, so that a robust tree, so that the clock will go sufficiently in the equal intervals of time to all the flops, and also there will be fan out split, so that the load will reduce on the clock port. Am I clear, team, till here? Hello.
Yes, sir. Yes, sir.
Okay. So, and yeah, there will be something called as HFNS, high fan out net synthesis, where not only the clock and also some static signals like preset clear, because preset clear are the signals that will go to many sequentials, and these type of signals will have high fan out. So these are also need to taken care regarding their fan out. So they also will they also get synthesized similar to as a clock. Clock buffer and normal buffer. Clock buffer, the rise transition and fall transition will be same. The normal buffer, the rise transition, fall transition might not be same, because in the clock buffer, the clock signal should have constant width or duty cycle. To maintain that, we need to have equal rise and fall transitions. This is how the CTS is done. You can see the robo from the PLL how the things got. You can have an internal PLL or external PLL, anything you can have. So basically in STA reports, you will be finding source insertion delay, network insertion delay. So network insertion delay will be coming like this. Like from the trunk buffer to the flop, the leaf level tree. Source insertion delay will come in the parent level tree. This is how the things will work. This is called anchor buffer, and this is called trunk buffer, and these are the leaf level sinks. These are called sinks or sink pins. So in the capture flop, if you have more number of buffers, it will result in a positive skew, and if launch flop you have more number of buffers, it will result in a negative skew. So ultimately, your CTS will try to balance the skew based on the timing violations. So there will be two types of skews. So there is global skew, local skew. Global skew is nothing but the highest insertion delay minus the least insertion delay in your clock tree. So if your global skew is high, that means your clock tree is not built that much robust. If your global skew is low, almost all the flops are reaching, are getting clock signal at the same point of time. And yeah, useful skews can have something nothing but see, you will have consecutive flops. So your
sir, yesterday in the yesterday class we have completed all this jitter and we completed.
Okay, sure. And I'll pass by. Yeah, CTS algorithms, like basically to distribute the clock in a very efficient way, we'll be having many types of algorithms. So it's something like depends on the situation where what type of design is yours and how to build the tree. Like if it is something like pipeline design, like all the sequentials are falling, in a candlestick patterns, then you'll sort of using the H tree, and if your design is very random, then you'll be using the RC tree, like that. It is completely based on how your sinks are placed in the design. Are they random or are they organized? So your tool is intelligent enough to pick one of these algorithms. These are all embedded in your CTS engine. These are all the utilizations of the CTS engine. And we come to routing. The routing will have the metal stacks like this, or the different. You can see three-dimensional metal stack. You can see the width increasing. Width sometimes most probably increases from bottom to top. It's not that sometimes it might remain the same, but it can never decrease. The top metal layer is greater than or equal to the bottom metal layer. This is how the routing will happen. I just showed you in a drawing, but this is how it happens. These are called wires and these are called metal layers. So global routing will be done. That is something like it will check the routability in the placement itself. Then track assignment will done after that, and then the detailed routing will be done. Detailed routing will try to fix DRCs and shorts if any, and yeah. And even the optimization also will happen once the route is done. There will be a number of iterations. And yeah, that's how the things get routed. Grid-based routing is nothing but your whole area of your chip will be defined, will be dissected into different grids, and each grid will be routing. Like if there are 10 to 15 standard cells in one grid, first those 10 to 15 will route, and then next grid will be, it will take the next grid like that. These are the metal resources. See, my metal is there only in the place of the track. If there is no track, my metal will not be there. So I need to be very resourceful so that I use all the tracks in an optimized fashion. Filler cells insertion. So to keep up the annual continuity and the density, uniform cell density, I need to add filler cells, and there should be no gaps in the base. In the base layer, there should be no gaps. I need to fill it by filler cells. Filler cells are nothing but physical cells. They doesn't have any logical information. Metal fills. Similarly, to maintain the metal density, I need to have metal fills. So uniform metal density, we need to have metal fills. So yeah, there will be some density rules. So based on that, you will be filling it with it. Because of following the density rules, while etching during the fabrication, there will be something called etching process. During this etching, right, things will be very good. Yeah, now coming to the packages. So basically, we'll discuss two types of packages. One is flip chip, and one is wire bound packages, which is very, very old fashioned packages. And next is flip chip packages, which is now happening. And there are also future enhancements and advancements. So this is how the chip looks. Okay. At the end of the session, we'll have a Q&A. Be able to discuss if any interesting questions or any questions. This is how the die looks. If you take out the top level thing, that's how it looks. This is a wire bound. You can see in the wire bound, you will have a planar arrangement of the ports like this. So your chip top will be facing to your face, and pins will be at the bottom in the wire bound. The top view of the IC, wire bond IC. Those are called bond pads. These are bonding wires, and these are bond pads. These will be connected to the bonding wires. So you will have a silicon wafer, and these are all the different dies, and one die is like this. Basically, we'll have very good dies in the center area of the silicon chip, and in the edges we'll have bad dies with bad performances. And so that's why there is some contrary, like the US and top NATO countries will be getting best dice from the shuttle, and these edge dice will be given to the countries, to the market, exported to the market, which belongs to a less powerful country or something like that. So that's why even so, if you take a phone, if you import a phone from Apple phone from US, and if you buy the same phone in India, you can easily make out the differences. Process variations, those are called the process. So why do we have this circular shape? Does anybody know the answer? See, because of the circle shape, many of my chips are getting wasted. My yield is getting wasted. But still, industry prefers the circular thing. Why? Any interesting answers? Hello, team.
More yield, sir. For more yield.
Actually, if I take a square, ma'am, so am I talking? Am I talking to? Am I talking to?
Sir, I am Kusma.
Yes, sir.
Usman. Okay. So if I take a square, that will give me more yield rather than
Yes, sir. But actually, maybe my answer is not correct. But the die shape is round because it is being sliced. For slicing the die, I think the shape it will be feasible.
wide. Okay. Okay. So the technology has enhanced very much, very big, especially the design and manufacturing technology. So why do people have to slice it in a circle? If they might have invented a very good technology to slice it in a square, right? Ma'am. So, like anybody, this is a very interesting question, and yeah, madam has given a very good answer. There is still some extension for that. So, okay, I'll reveal the reason. So, the thing is, if you so while preparing these dies, there will be a process where this particular slice have to rotate, in some thousands of RPM speed for uniformly distributing the dopants. The dopants will be, they'll try to put the dopants in the center, and to maintain the doping concentration uniform, they'll try to rotate it in some thousands of RPM. So while rotating, the moment of inertia is a sort of constant over the the radius. So basically from the center it tries to distribute. So if you have the radial direction, if you have a circular shape, then the centrifugal force will be equally distributed amongst the circle, among the surface area, and the force and that mechanical force it integrates over the small molecules of the dopants, and they will be equally distributed. If you take a square, there might be a chance like at the corners, I think more more dopants can go and sort of struck there, or there'll be a non-uniform distribution of the door of anything that happens in that rotation process in that speed. That is the most important reason for cutting it as a slices. So this is a 3D 3D chip connections. Now this is a fashion where especially there is a bottleneck between the read, write, and fetch cycle from the CPU to the memories. There is a bottleneck. So to avoid the bottleneck, they have to reduce the bus length or interconnect length between the memories and process. So the only way is to um, put the processor on top of put the memory on top of the processor like a 3D stack. So this is a new technology now. So after the dice, after the tape out, they will have some wafer map, like they will be testing, and the tested, the failed and successful dice will, you need to, how do you identify which die is successful and which die is failure? This is a problem statement, right? So you will have a wafer map matrix, and the tool will be able to identify what is what, and then they will be separating it. And gold, copper, and aluminum and silver are different interconnect materials that are being used. This is how the wire bond happens. And flip chip is something. This is wire bond. These are bond pads, and this is for flip chip. The flip chip will be reverse mounted, like the top face of the chip will be reverse mounted to the, you will not face the top of the chip, you will face the bottom of the chip, and there will be ball grid arrays like this, and your chip will sit on it. So yeah, and they will take care of that interconnects, and there will be also square grid arrays, like ball grid arrays and square grid arrays. Like the bump shape will be spherical for ball grid array, and the bump shape will be sort of cylindrical or cuboidal square grid arrays. The flip chip, this is the substrate, and this is a flip chip die. That's how it actually exists. Yeah, I'm open for questions if any.
Dear participants, now you can ask the queries.
Sir, I have a question.
Yeah, sure.
Sir, in your due course of experience, so how many tape outs you have involved?
I have done a couple of block implementations. That have been 3 tape outs in the block implementation and 2 full chip.
So my question is, what are the problems that you have faced in most of the cases?
The biggest problems you're asking?
Yes, sir.
Yeah, sure. The biggest problem that I have faced is, there is a design where it was very tough to fix the setup time. So
having related issues.
Yeah, setup violations. It was very, very tough to fix. There were lots and lots of setup violating parts. The whole was good. Yeah. So we initially thought the whole was good, and we overfixed the setup. Okay, in the CTS stage and then route stage, and suddenly there were some interconnect. There were some bottleneck parts where they were splitted out as a fan out, and that particular path that has splitted out as a fan out is failing as hold. Like the same cell through which my setup is failing has also failed another path for hold. So what we have done, we have added some buffers with, we have added some buffers, and we have tried to clear that hold. And for setup, what we have done, and for setup, we tried to swap the cells to the LVT. Finally, what happened? Everything was fixed. Everything was fine, but power blew up at the end. There was a lot of leakage power. So then we came up with a very unique methodology called TPS methodology. TPS methodology is called as total positive slack methodology.
Okay.
Like you can see power is also very important. So because we have a lot of timing violations in setup, we overfix the setup by reducing or by doing the VT swap from HVT to LVTs. So what happens when you VT swap from HVT to LVT? Your power leakage power will increase. So that became a trade-off there. And what we did, we tried to set a trade-off between the power and the timing by using TPS methodology. TPS methodology is nothing but you will try to fix all the violations, but you will also have some parts with very, very big positive margins, positive slacks. Okay, not all the parts will violate. There will
Yes,
be
sir. Yes.
with very, very huge positive slacks. So you will go to those parts, you will address those parts, and in those parts, if you have any LVTs, you will again reswap it to HVTs. So what will happen in this way? So wherever you have a setup margin, you're trying to you're trying to optimize the power by again swapping HVT. So that's how we reduce the leakage power also, and as well as simultaneously the setup and hold. So first we had setup and we overfixed it, we got hold, and then we fixed it, and again we got some setup. So and then we got some power. So everything was
Understood.
yeah.
Sir, what are the research challenges for academicians like us?
Research challenges for academicians, especially in the physical design aspect, you're asking?
Yes.
Yeah. I'll tell you a list regarding these research challenges. The first will be automation. There's a lot of manual work. You know, the tool is there, obvious, but for a physical design engineer to control the tool,
Automation in the sense, sir,
you need
you are
to
expecting to involve ML techniques, machine learning techniques, or
yeah, that is a very good insight. Firstly, there will be raw reports. Okay.
okay, sir.
There will be raw reports. For example, if there is a timing report, or if there is there will be a folder of reports.
So which will come from the RTL.
It will come from the tool.
Okay, sir.
So, an engineer need to analyze that complete folder. That folder might contain 3 or 4 files. For example, time design command in Innovus. If you give time design hyphen post CTS in Innovus, it will dump you the summary. It will dump you the all path groups timing reports, and it will dump you all individual path group timing reports. So, an engineer should go through all those files and understand about the timing. So here we can come up with some data visualization techniques. Right? You can first you can process the files, extract the relevant data, and make some bar graphs, some pie charts. These kind of things are not yet there in the tools also. That can make designer's life easy. And on top of this, there is one thing that I would like to say. There is no best answer in physical design or best solution in the physical design. Or there is, you can also say there is no right solution in the physical design. There is always a better solution. Because everything is a trade-off in physical design. So, in this case, we can come up with machine learning models. We can come up with machine learning models which will suggest the designer, new recipes or new ways or new methodologies based on the current situation of the design. So that machine learning model, if you integrate it with the tool, then it should interact with the reports that are being there in the tool, or it should be able to interact with the tool itself and get the reports for itself and then process the reports, analyze the reports, and then prompt the designer, okay, this is how your reports are there. Okay, so you need to, you need to do this, or you need to do that. I hope I'm understandable now.
Understood, sir. Understood.
So report processing, report analytics, data visualizations are the first stage of research that we need to focus. This requires two expertise. One is the subject expertise, three expertise. One is the subject expertise, tool expertise, and then coders. Very, very efficient coders. So these three expertise as a team in an academia, having a tool in hand, can literally, attract the industries. So if you develop a machine learning model that can actually process the reports and really prompt good suggestions, accurate suggestions, then that will literally be a product that, it is very viable in the market. Yeah.
Understood, sir. Thank you, sir.
Okay. Any other questions? Hello.
Hello, sir.
Yeah, ma'am.
Participants, if you have no queries, we can wind up now.
Yeah, sure.
Hello, sir.
Yeah, hello.
Sir, can we have any research on acceleration, sir?
Acceleration on what?
In PD domain, is there any scope of accelerating the process, sir? Speed.
That's a very good. That's really a very good insight. That's very good insight. Yeah, actually, you can come up with a sort of, server programming, I think. So we call it as GPU programming. Are you aware of GPU programming?
No, sir.
Yeah. So let us say your tool is a process that is being connected to 4 GPUs. Okay. So you need to, so your tool at a time, your tool will run some multiple process, and you need to do the GPU programming in such a way that you will be able to communicate with your tool process jobs, and we call it as jobs. In Linux, a process called as job, and you need to divide those jobs, go for write a code for load balancing, and then you need to pipeline them in such a way that all the 4 GPUs are utilized in a proper way to act, such that all the process multi-threaded and are multi-threaded and are parallelly processed. So that is one way, and yeah, it is all about the compute. You need to, if this is one way, like you can make use of the existing hardware and you can optimize the time. This is one thing.
Sir.
And the other thing will be like you need to design your own processor, as simple as that. You need to design your own, customized processor specific for this particular design. That's again reinventing. Yeah.
Sir, in RISC-V, which is available in open source, RISC-V processor.
Okay.
Can we add this concept of acceleration, sir? What you have said?
Yeah, you can add. You can try. Like for example, see, the CPU just has only an arithmetic logic unit, right?
Okay,
Any
sir.
complex process must be reduced to ALU. But if you really try to add some, DSP chips and for general purpose, and also some ML hardware ML chips.
sir.
For compute purpose, and those those types of accelerators, hardware accelerators we call, if they are
sir.
integrated along with your general purpose computer, then
Sir.
it will go very good. Basically, you need to understand what type of algorithms runs on these tools. Machine learning
Okay,
algorithms, very robust machine learning algorithms will run on these tools. So
Okay, sir.
yeah, so we need
Okay,
to integrate these customized ASICs along with the general purpose processor
Okay, sir.
to accelerate. Yeah.
Okay, okay, sir. Okay, sir. Thank you, sir.
Yeah. Okay, team. If there are any questions, I'll take, or else let's wind up. It's a great talking to all the faculty members of GVP. I feel I'm lucky to have this session with you. Yeah.
Sir, thank you so much, sir. Really, it's a wonderful session, sir. It's more interactive. On behalf of Department of ECE and our participants, I would like to express our sincere gratitude for outstanding session, sir. Your insights into the topics like logic synthesis, library setup times, netlist timing budgets, and virtual clocks were really interesting and very explanatory, sir. We appreciate the clarity with which you address the participants and the queries you clarified,
Yeah.
ensuring a deeper understanding of these critical concepts, sir.
Yeah.
Maybe this is a good takeaway for all of us, and we can focus more on the research perspective also.
Yeah.
Many of us are doing research in the VLSI domain, sir. Really, it is a good help for us. Thank you once again for your valuable time and effort and invaluable contribution to the success of this program, sir. We'll
Yeah.
definitely look forward your effort, your opportunities to learn from you in our future endeavors, sir. Thank you so much.
Thank you.
Yeah, your presentation is too good, sir. And actually, you have prepared so many slides, right? Due to the time constraint, it is not able to show all the slides.
Yeah. Like every concept is like is like an ocean, basically, to concisely to yeah. I think it would. I thought the session would be successful if I am able to put up most important points with clarity. Yeah. So my intention was not to explain all the slides, but whatever the important slides I have in that particular situation, I tried to explain it to the
Yes,
level
sir.
of interest.
Yes, sir. What are the topics you explained? It is very clear for all of us, sir.
Yeah. Thank
But
you so
but
much.
we can treat this as a basic and we can explore more.
Exactly. This will give rise to a lot of gateways. It will open
Yes,
many
sir.
gates. Yeah.
Thank you so much, sir. Dear participants, if it is possible for all of you, you can on the camera. Uday, sir, you also please on your camera. We will take a group photo, sir.
Sure. There's a sort of camera problem here.
Okay, sir. No problem.
Unable to do that. Yeah. Sorry for that.
Sir, please stop your presentation.
Okay.